hello everyone, welcome to class 15. So, we have been talking about Bravais lattices. So far we have sort of come through the laundry list of all the crystal systems that we have, and we stopped at the tetragonal system, right, yeah, and so we have counted up to 9 Bravais lattices so far. And so today we'll go to the next crystal system, which is the cubic crystal system, right. So, the cubic unit cell has A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees, right. And so how can we center the cubic unit cell such that by centering we actually see that this so the cubic unit cell comes, and then you have a threefold axis of symmetry about all the 4 body diagonals, but without centering you do not get that information, right. So, that is what we are trying to look at. And so I mean we can do the exercise of actually trying to start with a centered unit cell. If we start with a let us say a C centered cube, you will quickly realize that a cube so you cannot just have lattice points which are C centered, because so by definition this should have a threefold symmetry about all these body diagonals, and a threefold symmetry will take this centered face this face center to some other face center, right, and this face center to here, and so on and so forth. So, you will actually end up populating a C centered cube cannot exist, because threefold axes of symmetry, these are multiple axes about axis of symmetry, means that a 0 half half, if 0 half half exists, that means half 0 0 and 0 half 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 0 and 0 half 0 half, right, should also exist. You can sort of imagine it if you have some good intuition, right. So, if I am threefold, if I rotate this by 120 degrees, right. So, I am going to take this point and put it here, right. So, about this axis, if I am rotating by 120 degrees, so I will take this point and put it there, and so on and so forth, right. So, I start flipping the face centers around, and so so it is not possible if I just have a C centered cube, I cannot have threefold axis of symmetry, right. So, just a C centered cube does not exist. By symmetry, what we will have then is an F centered cube. Okay. Similarly, you can show that just an I centered cube also can exist, right. Having an F center will give you the unit cell which is cubic, which will otherwise not exist, right. So, otherwise so I can take an F centered, I can do exactly the same exercise that I did so far, right. So, I can take this face center, right, and then I can try to make a unit cell out of, okay. So, sorry, let me just draw this. So, I can take this face center, and the ensuing unit cell is not cubic, right. So, these angles are sorry, and the third face center also. So, I have to take the third face center and I draw a corresponding, I mean, so this is an exercise you would have done in so many other courses, where you take a cube and you take an a face centered cube. You take a face centered cube, join all the face centers with the corner, right. I will try to do that, but I am not very good at drawing. So, and then I have another face center here. So, I can so ideally I can define a primitive cell by just joining all the face by joining all the face centers, right, and then finishing that polyhedron, but that polyhedron is not cubic, that is not cubic. Okay. So, you will not see the 3 4-fold axis of symmetry if I construct a primitive cell, right. I mean, I am not doing it very rigorously, but so you can just believe me here. So, a primitive unit cell ensuing from a face centered cubic cell is no longer, I mean, does not show a cubic symmetry. Which means the unit cell does not look like a cube anymore. As a result, I do not understand that the underlying symmetry are 4 3-fold axis of symmetry, right. So, a face centered cube is necessary. So is an eye centered cube or a body centered cube. Right. So, in fact, these are two of the most popular Bravais lattices that one would have encountered. One is what is called the face centered cubic structure. I mean, these are for crystal structures, right. So, you put a motif and then call it face centered cubic, the FCC, right, but FCC actually represents the lattice centering, right. So, it does not so although we say, oh, that has an FCC structure, we confuse the crystal structure to be what is a lattice centering, right. So, lattice centering, the corresponding Bravais lattice is FCC, right. So, it is a face centered cubic, which means I have centered a cubic cell with face center, right. So, and then I put the motifs on all these things. Okay. So, to make the crystal structure, or I have a BCC, which is a body centered cubic structure, right. And so these are the most popular Bravais lattices that one would have studied. Okay. If I take the structure of let us say a metal such as platinum, right. So, platinum will have a crystal structure whose will have a crystal structure whose Bravais lattice is face centered cubic. Okay. So, as a result, so lot of metallurgists actually study a lot about FCC and BCC lattices, right. So, this is very popular in metals. Okay. Iron, right. So, for example, an iron carbon phase diagram, iron goes from a BCC structure to an FCC structure when you start heating it above a certain transition temperature. The BCC structure is what is called the alpha phase of iron, and the FCC structure is what is called the gamma phase of iron, right. So, anyway, so this is very popular among metallurgists, these Bravais lattices. Okay. Now, face centering, I am just going to represent it as F, as I said. So, C for cubic, F for C for cubic and F for face centered. So, this is how I am going to write my FCC. So far I have been saying, you may have heard people saying FCC, but in this course I am going to represent it as CF as the corresponding Bravais lattice, and similarly CI as your BCC Bravais lattices, right. You can also have a primitive cell, right. So, CP is the primitive cell, right. So, that is a simple cubic structure, right. So, these are the 3 Bravais lattices that a cube would add, right. So, now 9 plus 3 12, all right. How many more crystal systems do I have? I have a hexagonal system and I have a rhombohedral system. So, a primitive of course, both of them should have a primitive lattice. So, HP or the primitive hexagonal system is the other one, right. So, that adds to, that is the 13th Bravais lattice, and so a primitive RP, right. So, a primitive rhombohedron where I take a rhombohedral unit cell as I defined earlier, I will come to the caveat here, is the 14th Bravais lattice. Okay. So, can I not center a hexagonal? So, let us go to hexagonal unit cell and ask the question, can I not center it? It looks like there are it does not make any sense to center the hexagonal cells, right. So, why is that the case? So, that I can show from these pictures here. So, for example, what is the kind of centering? So, this is the hexagonal unit cell. I am just representing the basal plane of this, right, and then the c axis comes out of the page that you are seeing. Okay. Now, let us say I am going to center this at at all the so at these atoms sorry, these lattice positions. So these lattice positions are at the centers of this parallelogram, which means they are at positions of a by 2 plus b by 2, right. So that is some sort of face centering. Let us say if I am face centering it, right. So, just I am putting these red atoms everywhere, right. So, and I am face centering this hexagon. The ensuing unit cell is no longer hexagonal, right. So, I have 90 degrees here. So, what I get is an orthorhombic unit cell. Upon base centering a hexagon, right, base centering a hexagon, just like hexagonal unit cell. So, the symmetry, I mean, so it does not so it kills the 6-fold axis of symmetry, right. So, there is just by putting these additional lattice points, right. So, at the centers of so my unit cells, I am going to kill the 6-fold axis of symmetry. So, I would not do that, right. So, and what I have is an orthorhombic system. So, I go back to an orthorhombic system, right. So, centering a hexagon is actually killing the 6-fold symmetry. So, centering it this way. Okay. Similarly, you can also center it at c by 2, which is the other it is completely face and so all the c by 2. So, I am going to center this and this, right. So, I am going to also go along the prismatic plane. So, it is equivalent to face centering a hexagon. That is also going to give you an orthorhombic unit cell, and that is also going to kill the 6-fold axis of symmetry. So, you cannot center a hexagonal unit cell like you center a normal cubic unit cells, right. So, or trigonal or triclinic or monoclinic unit cells, right. So, hexagonal unit cells need to be centered a bit differently. You cannot just put lattice positions at c by 2 or a by 2 or b by 2, right. So, that will kill the 6-fold symmetry. Now, what you can however do is what we did when we were defining a rhombohedral unit cell, right. So, if you remember that, we were actually centering the hexagonal unit cell like this, right. So, we were putting atomic positions at 1 by 3, 2 by 3, 2 by 3, and also 2 by 3, 1 by 3, 1 by 3, something like which is represented in all these figures sort of represents something very similar, right. So, I have 4 hexagonal unit cells, and if I am putting the open circle at 1/3, 2/3, 2/3, I have these 4 points that are covered. If I am putting the closed circles at 2/3, 1/3, 1/3, I have these closed points that are covered. One is at a z equal to 1/3 plane, and the other one is at z equal to 2/3 plane, right. And then what I do, so this is some sort of centering of the hexagonal unit cell. Right. What ends up happening here also is that I kill a 6-fold symmetry, right. So, I do not have 6-fold symmetry, right. But if 6 bar is so, but I get to a 3-fold symmetry, but again there is some vagueness there, because 6 bar has a 3-fold symmetry in it, right. So, so there is no real 6-fold symmetry, but it is 3 by m sort of thing. There is a 3-fold and an m sort of thing, right. So, I can get to so I can again, so it is the same way in which I have defined earlier a rhombohedral unit cell. So, I can join the AR, BR, CR which are shown here, right. So, those are here, and I can join this one, and I can make a unit cell, and this unit cell is nothing but a rhombohedral unit cell. Right. So, in general if I am centering a hexagonal unit cell in the proper way, either I kill the 6-fold axis of symmetry or so centering a hexagonal unit cell kills the 6-fold axis of symmetry. Right. You can center it any way possible, you are always going to kill the center 6-fold axis of symmetry. However, you center it in a specific way, right. So, you center it. Now, this centering we did not study, this is not face centering, this is not body centering, right. So, for hexagonal unit cells you have to center it in a specific way. If I am centering it about 2/3, 1/3, 1/3 and 1/3, 2/3, 2/3. If these are the lattice points of centering, well, I can still get go from 6-fold to something like 3-fold symmetry. However, that ensues so what comes up from this centered hexagonal unit cell is a rhombohedral cell. Or in other words, I can define in this 3-fold symmetry, I can define a rhombohedral cell, a primitive R cell which carries information about 3-fold axis of symmetry. So, it does not make sense to center a hexagonal cell, because assuming that so the basic tenet is that hexagonal cell has an underlying 6 or 6 bar symmetry, right. So, now if there is a 6-fold operation symmetry operation which lets me define a hexagonal cell, well, by centering it I always kill the 6-fold axis of symmetry, right. So, in that context I cannot center a hexagonal cell. So, that is why all I have is a primitive hexagon, right. So, HP. Okay. Now, if I manage to center it and center it in this fashion, right, I can get to a primitive rhombohedral cell, right. So, primitive rhombohedral cell I can define that as a proper unit cell. Okay. I can go there, but primitive rhombohedral cell looks like a centered hexagonal cell, but so you have killed the 6-fold symmetry, you have come down to 3-fold symmetry. Okay. But so I told you in my earlier class that a rhombohedral cell, a rhombohedral structure, you can either use to represent this, you can either use a unit cell which is a primitive rhombohedron, or a centered hexagon, right. So, we looked at that. So, the other way of representing a rhombohedral structure is you take a hexagon and then you say a rhombohedron is nothing but a centered hexagon, right. So, people do both notations. So, you can use a primitive rhombohedron which is AR, BR and CR, or a centered hexagon which is AH, BH and CH. These are related in a certain way, but a centered hexagon can represent a rhombohedron, not a 6-fold symmetry, can represent a 3-fold axis of symmetry, right. So, fundamentally by centering a hexagon I always kill the 6-fold axis of symmetry. So, the only Bravais lattice I have with hexagon is a primitive lattice, right. But the only Bravais lattice I will have with rhombohedron with 3-fold symmetry is also a rhombohedral Bravais lattice, a primitive rhombohedral Bravais lattice, if we follow the rules accurately, right. So, that we do not so the simplest unit cell that has the least number of lattice points is that represents the symmetry, the underlying symmetry is my Bravais lattice. If I follow that rule, then I should just have a rhombohedral primitive cell, right. So, that completes my 14 Bravais lattices. However, you would more than often keep seeing that people represent these rhombohedral unit cells in hexagonal notation, thinking of it as a centered hexagon, right. It's so everyone does it. So, it is not completely technically correct, but everyone does it. So, because of convenience, because I can just use a unit cell with 120-degree angle with respect to each other, and then the c axis. So, I can say what the c axis is, which is now a 3-fold axis of symmetry, not a 6-fold axis of symmetry, and I can have a basal plane, and I can have my language developed after the hexagonal crystal systems, right. So, it is not wrong, but but that does not add to an extra Bravais lattice, right. So, all in all you have 14 Bravais lattices, and we have counted all of them, right. Okay. Which help you keep the symmetry, I mean which help you detect the symmetry of the system. If I say I have Cp, I know that okay, this is sorry, or Cf, I know that this is an F face centered cubic, and so the symmetry that should be there in the underlying lattice is at least 4 3-fold axis of symmetry. Okay. So, now just to represent, I can go to the next slide. So, these are all the 14. So, I start with the triclinic AP, I have MP, MB. So, 1 plus 2 plus orthorhombic, I have 4 of them plus 4, right. So, tetragonal I have 2 of them plus 2, then hexagonal is 1, trigonal or HR, this is 1, right. So, and then cubic is 3, right. If you see here, they have represented the hexagon sorry the rhombohedral lattice as the HR. So, it is still represented as a centered hexagon, rhombohedral centering of a hexagon, that is what it means, right. So, because here this is face centering of an orthorhombic cell, this is primitive centering, or this is eye centering of a tetragonal cell. So, similarly you interpret this as rhombohedral centering of a hexagonal cell, but you can also look at it as just P, which is primitive of a rhombohedral cell, right. So, both are equivalent. Okay. So, this is the more accurate thing, because so you actually get so just a 3-fold axis of symmetry. The 3-fold axis of symmetry is represented here, not here. Okay. All right. So, so with that we finished our discussion on Bravais lattices. I will keep the, and then we can actually go on and understand what point groups are. For the next 10-15 minutes, we will look at, we will start our discussion on what point groups are, right. So, just to recap, we said there are certain operations, certain symmetry operations we have in our materials, and so we can classify all our so crystals essentially, so materials which are crystalline in nature, into crystal systems, but these crystal systems actually come from underlying symmetry operations, and we have looked at a few of these symmetry operations, which are rotations, roto-inversions, mirrors, inversion, etc. Right. And we said so an underlying symmetry operations, so the crystal, if I talk about a crystal system, all crystals can be classified into 7 crystal systems and 14 Bravais lattices. Bravais lattices because you can center these crystal systems, right. So the crystal systems have a particular peculiar unit cells that you can pick among all the different unit cells that you can define, and this unit cell should represent the underlying symmetry, because underlying symmetry is what dictates what the crystal system is. If I have just one 2-fold axis of symmetry, I will say it is monoclinic, right. So, I will blindly say it is monoclinic. If I have 4 3-fold axis of symmetry, I will call it a cube, a cubic symmetry, but if I have 1 3-fold axis of symmetry, it goes to a trigonal crystal system. Okay. So, crystal systems are intricately related to the symmetry, right, to the symmetry operations that we have studied earlier. Right. Now, the question is, so earlier we and then so are the Bravais lattices. So the idea of defining a Bravais lattices is so that in a unit cell, in the preferred unit cell that you are defining, you keep that symmetry, right. So you understand what is the underlying symmetry. Okay. Now, okay, so be that as it may, so far we have been looking at symmetry operations which is a 4-fold axis of rotation, or 4 bar symmetry operation about a point, etc. what happens if you combine some of these symmetry operations, right. So my system, my crystal system, or my material now shows certain points about which there are several symmetry operations, not a single symmetry operation, right. So these several symmetry operations come under the purview. So just adding on several symmetry operations at a single point or at a particular point come under the purview of what are called point groups. Okay. Groups, because so groups has a particular mathematical connotation to it. So all the point symmetry operations that act through a particular point in a crystal, so they all follow what is the mathematics of what is called a group, right. So I am not going into the group theory here, right. So which is again so it is a mathematical field by itself, right. But I will just define what a mathematical group is and say that all the there are what are called point groups which define a set of symmetry operations about a point, and all these form what is so mathematically you can discuss them as what is called a group, right. So and group is a mathematical term, right. So first I will actually define what a group is and argue to you that if there are certain symmetry operations, certain other symmetry operations belonging to the same group should also exist about that point. Okay. Now point, you understand, point is a specific point about which symmetry operations exist, and what is a group, right. Now group mathematically is defined as certain properties, certain set of properties of the group, right. So for example, if I have P, which is an operation in a group, a rotation let us say, and Q, which is another operation in the group, and this is 4-fold rotation, this is 2-fold rotation, right, about a point, P, Q are members of S, right, S being your group, S being your point, so I mean I am going to actually define what a group is. So I do not want to, S being your set for example, right. So I do not want to be cyclic and then say S itself is a group, P, Q are members of a group, no. So I am going to define what a group is. A group is something that has all these properties. P and Q are operations in a set S, then P, Q is also a member of set S. Okay. So that is the first property of a group. If P and Q are members of set S, then P, Q is also a member of set S. Okay. Then a group should have an identity, or in other words P times 1 should be equal to 1 times P, that is equal to P. Okay. So that is an identity operation. Now a group should also have an inverse. Right. So in other words, so if there is P, there should be a P inverse such that P times P inverse is your identity 1. Okay. So for example, if I take a rotation, let us say 6-fold rotation, right. So if I do 6-fold rotation, so I go I go clockwise, sorry, I go 1 6-fold rotation, I go anti-clockwise by an angle of 60 degrees, right. Means anti-clockwise rotation by 60 degrees. Now what is 6 inverse, or what is the inverse of this operation? It will be a clockwise rotation by 60 degrees, right. So if I have 6 and the inverse of 6, right. So these are this will be represented as 2 different matrices, of course. You get back, so you rotate something by 60 degrees and come back by 60 degrees, right. So you are coming back to the same asymmetric unit, right. So this is an identity is 1 actually, not I. Okay. So an inverse should exist, right. So that is the definition, I mean that is what happens in a group. and also associativity, right. So, there is the property of which is if I have P and Q and R are members of the group, so I can operate R first and PQ next. PQ times R is equal to actually P times QR. So, or I can operate QR first and then P next, right. So, this is associativity. Okay. Now, you can also so there is in general in a group there you do not need to have commutation. So, commutation is, it does not matter which operation you operate first, QP should be equal to PQ sorry QP, right, but this is not necessary to exist in a group, to have in a group, right. So, we have what are called abelian groups where the commutation exists, but not in every group. So, I am not really sure if all point groups are abelian groups, but lot of them are, right. So, I will need to check that up, but in general this is the mathematical structure of the group, and this sort of we have used something like the first property we said. If my orthorhombic system has two two-fold axes of symmetry, the multiplication of it gives me a third orthogonal two-fold axis of symmetry. So, that also should exist, right. That also should exist means I said about that point, if there are two two-fold axes of symmetry, right, then that defines an orthorhombic system. In that discussion I said there should be a third axis of symmetry which comes for free, right. So, that is just the property of the group, right. So, if I have two operations, their product also should be a legitimate symmetry operation that is happening that occurs through that point, right. So, that is as simple as that. Okay. So, so you have points about which there are groups of operations that exist, not a single operation, and these groups, and hence what you have are symmetry operations which can be classified as point groups, right. So, just like 2, 2 and 2, right. So, along a point I have two-fold axis of symmetry which is in x direction, two-fold axis of symmetry in y direction. That means the multiplication of those two operations which are representable as matrix, which is two-fold along 1 0 0, two-fold along 0 1 0. So, I should have two-fold along 1 0 0 1, right. So, that also is a legitimate point group operation, and that also should exist, right. So, in that point group that should exist. So, if my crystal has a point group 2 2, it is given that the crystal should have a point group operation 2 2 2. Okay. So, sorry, it should have a point group, not an operation, it is a set of operations. Okay. So, it should have point group 2 2 2. Okay. Anyway, so we will actually look more carefully about all the various point groups that come up, but turns out that in all these three dimensional crystals I can classify all the different point groups, but these point groups so come up from operations such as 1 2 3 4 6, right. So, these are operations, symmetry operations, or 1 bar, 2 bar, 3 bar, 4 bar, 6 bar, right. So, these are symmetry operations. So far we have seen them as single operations, not as combination of several operations, right. So, these are symmetry operations, but all these operations are compatible with translational symmetry. Or periodicity, right. So, or periodic nature of crystal. Right. As a result, so what we are looking at are point groups. So, what we are looking at are point groups which are set of these operations, right. So, you have multiple of these operations, not only one. You can have one, but so you can have multiple of these operations which are just compatible with translation. Okay. So, these are actually called not just point groups, but these are crystallographic point groups, because by crystallographic I mean that they are compatible with translation symmetry, right. So, crystallographic point groups. Okay. And next, in the next class I am going to show that we have 32, only 32, or different point groups, right, and all sorts of crystals will have one of these 32 different point groups, right. So, so we will have points of different symmetries, of course, but each of these points, special points, you cannot have any other symmetry operations other than these 32 symmetry operations, combination of symmetry operations, right. So, 32 different point groups, right. So, all crystal classes can be divided into 32 different point groups. Okay. Okay. So, so point groups are very important, because so later on we are going to say there is a point group in a crystal, but then point group plus translation symmetry. Point group is just about a point, right. So, but in a crystal there is also translation symmetry. So, if I add the caveat that I have point group plus translation symmetry, I go to what is called a space group, right. So, space groups I am going to talk about it very briefly in a couple of classes from now, but so point so the important thing that defines our properties are the corresponding so any space group, every crystal will have a space group. So, every material will have, every crystalline material will have a corresponding space group, right. So, associated with it. Now, for every space group there is an underlying point group. We will see what this underlying point group is, and this point group is what determines the properties of the materials, right. This is the Newman principle, which we have discussed a bit earlier, but I will keep on repeating it, right. So, to connect all these symmetries that we are doing with respect to the properties of the material, we have to really understand the most important thing to understand are the point groups, not necessarily space groups. Okay. So, point groups and realization that every space group has an underlying point group, right. Anyway, so these may sound like words right now, right. So, dry words. We will put a structure to it in the next two classes, and eventually go into space groups. Okay. All right. So, with that I conclude this class, and I will see you all in the next class. Thank you.